A 3-foot spring made of flesh, bone, and wood conquered a staggering 12 million square miles of global territory. These pink boundary lines show the scale of that expansion, reaching from the Sea of Japan to the borders of modern-day Hungary. Dominating a landmass of this size required a specific mechanical advantage over every other military power of the 13th century. To find that advantage, we can look at the recognizable benchmark for ancient artillery, the English longbow. This weapon stands 6 feet tall and requires roughly 150 pounds of pull force, the draw weight, to store 100 joules of energy. This chart compares that massive 6-foot bow against the standard weapon of the Mongol cavalry. The Mongol bow is half the height, yet with that same 150-pound draw weight, it stores a staggering 200 joules of energy. It delivered double the energy density of its European counterpart, while remaining small enough to operate in the saddle. In the 1200s, this ratio of size to power recalculated the odds of medieval warfare. A single piece of wood cannot survive this much energy storage. If you make a wooden bow this short and pull it this hard, the stress exceeds the material's breaking point and the limb snaps instantly. This cross-section shows how the Mongols bypassed the limits of wood. They used a thin wooden core as a skeleton, then glued a layer of water buffalo horn to the belly. Horn is exceptionally dense, allowing it to store energy while being squeezed under massive compression. To balance that pressure, they applied animal sinew to the back of the bow. These protein fibers act like thousands of microscopic rubber bands, stretching under extreme tension to store the energy that wood alone would reject. These layers were bound with fish bladder glue, which required an immense amount of time to stabilize. From first assembly to final curing, a single bow took up to 2 years to manufacture. The Mongols sacrificed manufacturing speed for mechanical efficiency. Their bow wasn't a tool that could be carved in a day. It was a highly engineered weapon system that took a year to mature. This complex engineering was driven by a single tactical requirement: the saddle. A 6-foot longbow is physically impossible to maneuver over a horse's neck during a charge. To be mobile, the bow had to be compact. This vector diagram illustrates the Mongolian thumb draw, which solved the problem of pulling a short bow to a long distance. By hooking the string with the thumb rather than 3 fingers, the archer can pull the string 32 inches back, well behind the ear, even on a short-limbed weapon. Mastering this required a lifetime of conditioning. Mongol warriors trained from childhood to balance at a full gallop, steering horses entirely with their legs so both hands remained free to operate the weapon. This mobility allowed for the arrow-storm tactic. Instead of individual aiming, units fired up to 12 arrows per minute at high trajectories, saturating a predetermined area with plunging fire. The bow's small size also enabled the Parthian shot. This carving shows the specific biomechanics required to feign a retreat, then suddenly twist in the saddle and fire accurately while aiming backward. The weapon was only effective because it existed within a closed loop of human training and animal mobility and composite engineering. However, this engineering had a specific environmental limit. The very glues that held the bow together were water-soluble. In the high humidity of Southeast Asia or the persistent rains of deep Europe, the organic adhesives would soften and absorb moisture. When the glue failed, the horn and sinew would simply peel apart, rendering the weapon useless. Beyond the weather, the bow faced a new physical barrier: thicker steel plate armor. By the late medieval period, metallurgy advanced, and even a 200-joule arrow struggled to pierce a solid steel chestplate. This musket barrel represents a shift in raw power. While a master archer took a lifetime to train and produced 200 joules, an early gunner could be trained in weeks and deliver over 2,000 joules of energy with a single pull of a trigger. The composite bow wasn't replaced by a more sophisticated bow. It was defeated by the brutal energy and training economics of gunpowder. Today, the composite bow is no longer a martial necessity. It is a cultural tradition kept alive on the steppe by practitioners who still study the relationship between the horse, the rider, and the bow. For a few centuries, this specific combination of materials allowed nomadic armies to outshoot the largest sedentary empires of the age. It was a weapon designed for a specific way of life, and it used the laws of physics to change the map of the world.